Okay, thank you. Okay. Okay, awesome. Okay, hi everyone. My name is Lyra, and I am a postdoc at Vanderbilt University. And I'm going to be giving an initial review on lithium depletion and its particular applications in premium sequence stars and how we can use it for a whole host of really cool science. I would like to thank also the LSC and SSC for giving me the opportunity to give this talk. So lithium is really cool. It's a fragile light element, and in premium sequence stars, we get it and then we get to burn it. And that burning process is really diagnostic for us because in order to kind of observe patterns of lithium depletion, we need the story to go something like this. We need to destroy it at 2.5 megakelvin or thereabouts. And stars reach this at different points in their evolution in a mass-dependent fashion, and a whole bunch of different physics can affect when you start destroying your lithium. This temperature that lithium gets to when you burn it on the premium sequence is reached at the base of the convection zone, which means that you actually have to mix the material down there in order to deplete it and then see it in depletion on the surface abundances. So as a result of all this different physics together, we can actually look at lithium abundances and use it to test different processes in stellar physics, including mixing, including burning, including what the stellar interiors look like. And it can also be used as a very useful and sensitive age diagnostic as well. So I wanted to talk about some of the really cool stuff that's being done right now with lots of new surveys that are coming online, lots of new data coming in from these large spectroscopic surveys. Here's the EGLIS project, kind of led by Rob Jeffries and collaborators, using Gaia ESO data, looking at a whole bunch of these different stars from clusters. And so you can see these are lithium depletion patterns. On the left-hand side, this is Kepler's lithium equivalent width, and you can see that the points are color-coded by their age. You can see that there are patterns in the colors that kind of pop out in this diagram. And building these kind of empirical libraries, such as on the right-hand side, empirical models about lithium equivalent widths deplete over time is incredibly useful because this gives us a technique to actually
people pointed out that they can't hear in the back. I would like to point out that there's front.
Okay.
But
Okay.
I don't know if there's a volume knob.
Is there a volume knob?
Speakers or just a Zoom?
Okay. It was starting to slip on the lanyard. Okay. Okay. I'll just hold it up like this. Okay. Sorry. Okay. 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 So the usage, the building of these empirical libraries and these from these large surveys has enabled us to start tracking the depletion of lithium and start looking at it systematically in an age-dependent fashion from the empirical side. And I want to specifically highlight the talk coming up from George Weaver using these age tag stars and neural networks to then infer precisely for a whole bunch of these stars what their ages are from lithium. I want to also highlight the work done in SDSS-5. This is a whole bunch of spectra taken by the survey, the BOSS survey instrument. And I want to highlight Marina Kunkel's work and also the poster by Surat Saad. This is related to the Apogee and BOSS Young Star survey. This is looking at equivalent widths. And here are a whole bunch of these lithium depletion patterns, but they go to really young ages. And these are specifically targeting super young ages, starting to really disentangle the lithium pattern and the lithium depletion pattern as it occurs in the youngest ages. I also wanted to talk to shout out kind of the opportunities for testing stellar physics in with lithium, and this is kind of GLA data, and this is the talk that Tibble will give coming up. This is basically looking at how our stellar models with angular momentum transfer and mixing can actually give us diagnostics into what lithium abundances look like as a function of Fe on H on the x-axis. I also wanted to talk about kind of how we also disentangle the impact of magnetism and rotation. This is work done by Alex Binks. On the left-hand side, this is a color magnitude diagrams with a whole host of different magnetic field strengths that basically star spot filling fractions. On the right-hand side, these are kind of lithium depletion patterns. On the top, we can see that this is at fixed star spot filling fraction varying the age. On the bottom, we can see this is at fixed age with different star spot filling fractions. And we're starting to be able to disentangle the impact of magnetism and age spreads in some of these young clusters by having this independent activity data and starting to look at the outputs of these theoretical models. Look out for Alex Binks' talk on mapping lithium and rotation for a bunch of these open clusters. So this is all really super cool stuff that's coming out from these giant surveys. But I wanted to return specifically to the lithium depletion pattern and start to disentangle some of the different parts of it. So we can see on this diagram, this is another lithium depletion pattern. On the x-axis is TEV, on the y-axis is the abundance of lithium. And what we can see here is that the points are color coded by the surface velocity, rotational velocity, and you can see that there's kind of a color gradient in points. And the underlying line is an isochrone age to the age of the cluster. This is the Pleiades. And so you can see that there are points that kind of deviate from the line in really interesting ways. And this is in a rotationally dependent fashion. And so this is not a prediction from standard stellar evolution theory. This spread at constant TEV that spans something like 2 decks at fixed TEV. It's not something that can get out of standard stellar evolution theory. And also it has characteristics where the rapid rotators are systematically enhanced in their lithium. They're lithium rich. Now, keeping in mind that the standard models predict no spread at fixed TEV, and the fast rotators are lithium rich, this kind of contradicts our expectations of what rapid rotation ought to do, because rapid rotation ought to, from first principles, enhance the mixing and deplete more lithium. So there have been a whole host of these different explanations that people have given in the literature to try to explain why we see this spread in all these young clusters. Here's another example from Rob Jeffrey's 2021 paper. This is M35, kind of a Pleiades analog almost. So we have explanations that range from like different dislocking mechanisms for some of these stars in the pre-main sequence. We have ideas where rotation may be able to suppress mixing to some degree. We have ideas that maybe some of this may not be a real spread. Some of this might be due to solar activity and differences in the line formation parameters. But what I'm going to be talking about is the idea that maybe star spots and magnetism, the fact that star spots and the convective suppression, the suppression of convection in the outer regions of the star may actually cause the structure of the star to change and therefore impact the lithium depletion pattern. So in order to get to this picture, I want to talk about 3 steps that we take in order to self-consistently deal with the idea that these stars have inhomogeneous surfaces and that star spots and magnetism may affect all of these different parts of it. So the first thing that we do is that we generate theoretical models that account for star spots. These are the spots models, and these are public and available. These are models in which we assume that the surface boundary condition is modified by an inhomogeneous surface where you have spots covering some amount of it. And that inflates the star, that changes the, we also change the flux distribution on the outer layers, and therefore the star has a structural response to the fact that it has spots. Part of the stuff that I did in my PhD thesis in number 2 is that I recovered star spot filling fractions by assuming a 2-temperature template for recovering star spot filling fractions from spectra and apogee in a whole bunch of these stars. And it turns out that you actually can get a whole bunch of these really precise star spot indicators, star spot filling factors from a whole bunch of these high resolution spectra. But the third thing that we consider in this work is the idea that the equivalent widths that you measure, if your star has visible spots, the cooler component and the hotter component both contribute to the equivalent width in interesting ways. So this is the idea that perhaps because these stars have spotty surfaces, we should actually consider our measurements and interpret our measurements in the context of them having spotty surfaces. And once you do all these three things kind of self-consistently, you start looking at some of these relationships. So here is all of our data in the Pleiades. Here's in the 2022 paper. On the x-axis, this is Rossby number. This is rotation period divided by convective overturn timescale. This tells you roughly how rapidly rotating your star is relative to its structure. Low values correlate with with stronger dynamo numbers. So you expect magnetic activity to rise as you go towards the left, towards rapid rotation. And one characteristic of all these models of this data is actually you get kind of this decline at slow rotation and you get a saturation at rapid rotation. And this is a general feature that we see in a whole bunch of these activity relationships. So we take this data, this measured f-spot value with error bars, and then we kind of look at it in the lithium depletion plane. So on the left-hand side, this is a kind of a theoretical lithium depletion plane, except for the TEF, I guess. So you have ALI on the y-axis, you have a TEF on the x-axis, and we plotted here a whole bunch of single stars and binaries. So we exclude the binaries because the binaries have a more complicated solution. Either there are many stellar surfaces if you assume that each star has potentially a spot and an ambient solution. So we consider only the single stars, but then we plot underneath it the non-spotted or classical solution. And on the right-hand side, now I'm going to plot the spots isochrones. I'm going to color code them by the spot filling fraction predicted by theory. And then I'm going to overlay on them the star spot filling fractions colored for the abundance of lithium that we get from our observations. And so what you can see is that underlying we have a whole host of these star spot filling fractions predicted by theory. So we have the colors corresponding to the star spot filling fractions that we actually measured in these stars. You can shift these stars up and down vertically based on the differences in the interpretation of their curves of growth, because you're actually seeing the spot and the non-spotted surfaces of these stars, and you shift them left to right based on the effects of spots on their temperatures. So if you actually have two different temperatures on your stars, due to the spot component and the ambient component, fitting a single temperature solution to it may not, in fact, giving you the most accurate solution. And so we can actually now quantifiably test whether the lithium depletion patterns match between our theoretical models and our actual observations. This is what you can do now with kind of the leopard catalog. And the story that goes with it is that these rapid rotators are more heavily spotted, and therefore they're more inflated. They're cooler at the base of the convection zone, and they have subsequently reduced lithium depletion as a result. And so we have this result. We have this empirical pattern that the star spots that we observe in these stars correspond very nicely to theoretical predictions, can we actually take theoretical star spot models and reproduce this spread um, just uh, just normally? And so the thought experiment that we take is that we initially start off stars with a whole bunch of star spots. Then we turn off the star spots at some time. And if we turn off the star spots significantly before lithium burning occurs, then the end result lithium abundance will mimic that of a star that has never had spots on it. But this situation can change if you actually switch off the lithium burning during the epoch of lithium burning or afterwards. And so if you take these models, actually star spot models do seem to be able to produce um, uh, lithium depletion patterns that expand and fill this range with standard fast and slow rotator sequences. So we've taken fast and slow rotator sequences from the Pleiades, and we've simply on the x-axis on these bottom plots, we have mass. On the y-axis is abundance of lithium again. These are the lithium depletion patterns. But what you can see here is that with different values of the critical Rossby number, the point at which stars stop being saturated in their activity, if you change this value, you can actually get a separation between the fast and slow rotator sequences, where you have the slow rotators and the rapid rotators in the correct places for their lithium abundances to be explained from magnetic models. And the end result of this, so basically all these plots down here, these are mass on the x-axis, and this is the time at which the lithium, the time at which we turn off the star spot, the magnetism in the star. We actually predict that there ought to be a lithium rotation activity relationship that differs between the slow rotators and the rapid rotators in such a way that, you know, the colors here indicate the discrepancy between these models and a classical model. You have all the slow rotators up here with cooler colors, which indicate the discrepancy is that they mimic almost a non-spotted model. And so you have all the slow rotators and the rapid rotators kind of create that dispersion, and you can create the Pleiades lithium spread in that fashion. And so we can do this. We can do this with an enormous amount of data now, because now we have an enormous amount of star spot filling fractions and equivalent widths of lithium from all these different surveys in synergy. And so we can now start to probe mixing, burning interiors and stellar ages with this leopard catalog that we have now. And so just to summarize, we are now firmly in the era of large lithium surveys. We are starting to uncover relationships between lithium rotation and activity. Lithium can really be affected by the prior history of magnetism in stars. And that can actually really affect how much depletion of lithium that you have on the star, because it affects the prior radius, the prior convective, the prior temperature at the base of the convection zone. And so now we're starting to be able to test stellar evolution, start to link activity with this whole picture. We're starting to be able to do this for a large number of stars. Thank you very much. The way I can see the question. Oh. Yes. So, the question is there a correction, due to the fact that we have two temperatures in the actual, lithium expressed in the models, right? So we have predictions of the abundance of lithium, ALI. We can transform those to the equivalent widths, fairly trivially because we, have set for these models what the star spot fill infection ought to be. So we can directly produce, equivalent widths in that fashion.
And, who had the toxic,